Good morning, everyone. My name is Zenna Tavares. I'm an nth year graduate student at MIT. And today I'm going to talk about this project that we've been working on for a while, and it's about running programs in reverse. And so this is what work done with my advisor, Armando Soledazama, and my collaborators, Lawrence, Edgar, and Javier. So this talk's divided into, three parts. In the first part, I'm going to give you some science, some psychology experiments that people have done over the last 30, 40 years. And it's really about this idea of mental simulation. And as the name suggests, it's about how you simulate things in your mind. And then I'm going to give some theory about an approach that we're developing, which we call parametric inversion, which is about running programs in reverse. And then I'm going to show you some code and the framework that we're working on in the Julia programming language. So, in part one, I'm really going to try and build a case. And the case I'm building is for this idea of mental simulation. So I really want to convince you of three things, really. One, that there's a large body of experimental evidence which suggests that mental simulation is a core part of human intelligence. And two, that in order to build AI that's more general than the AI we have at the moment, we're going to need to emulate or copy this idea of mental simulation in machines. And three, that it's a really hard problem. So, as far as I know, the first study which has approached this quantitatively was in around 1970. And rather than tell you the experiment, we can actually do the experiment here live. So in these two holes, in the next slide, you're going to see two geometric-like objects, Lego-like objects. And they may be the same object, but from slightly different or very different orientations or rotations, or they may be geometrically different shapes. And so what I want you to do is when you see the objects, as soon as you're sure, just shout out same if you think they're the same, or different if you think they're different. Make sense? Okay, so A, same or different? Same? Well, it's actually the same object, yeah. Different rotation. Same or different? Also same? Some uncertainty, all right? It is the same object. We'll do one more. Same or different? Different, same? Same? So I think we can say this one's different. I think it's different. I didn't do this study. And so they did this with, I think, 1,600 people, and they showed them many more examples. And they did two things. One, they precisely varied the displacement and rotation. So some of them were very similar rotations, others were much more different in terms of rotation. And also they measured the response time, how long it took people to answer the query, same or different. And they found a linear response. Right? And so what this means, if you don't know what linear means, it means that if I double the angle of rotation, it takes you twice as long to answer the query on average. And as you can see, so these handlebars, they represent the variance. So as you increase the angle, people become, there's more, the correlation is less tight. But as far as psychological experiments go, this is a very tight correlation. Right? And so this led to a whole kind of subfield of similar experiments. So for example, some people call this mental animation as a kind of more general concept. And so I can ask you, if I rotate these two gears inwards, will the knob on the left-hand side mesh with the groove on the right-hand side? Yeah, probably right. If I give you two glasses of different diameters but filled to the same height, and I tilt them, which, if any, will the water come out of first? Any idea? Same? I'll leave you to think about that one. And if I let go of this, I let go of the free end of this system, will the lowermost pulley, would it rotate clockwise or anti-clockwise? So I don't actually know the answer to this question. I haven't looked, right? But they have, they did a similar paradigm. They asked people these questions. They measured their results in terms of response time and sometimes where they look in terms of the scene. And they built up more and more evidence that the way that people answer this question is the way that you probably feel that you're answering this question, right? You look at the image, you do some kind of simulation of the thing in your mind, and then you use that to answer the question. So, I think it's kind of cool. So, but why am I talking about it? And why am I talking about it here at Strange Loop? So the reason it's important from a psychological perspective is because it provides, concrete evidence for a psychological concept. But can we make this idea of mental simulation more precise? And so let's use some philosophy. So 50 years prior to this, prior to any of these experiments, a philosopher who's often credited as the founder of this idea, he put it like this. He said, if the organism carries a small-scale model of external reality and of its own possible actions within its head, it is able to try out various alternatives, conclude which is the best of them, react to future situations before they arise, and in every way react in a much fuller, safer, and more competent manner. And that sounds like a good thing, right? And before him, a physicist, Hertz, who you may have heard of, he was thinking about the same thing. And he said, we make for ourselves internal images of symbols of external objects in such a way that the consequences of the images that are necessary in thoughts are always images of the consequences of the depicted objects that are necessary in nature. We can quickly develop from them, as if from models, the consequences that in the external world will occur only over an extended period or as a result of our own intervention. And so what they're basically getting to is the idea that you look at the world, you build a model of the world in your head, then you interact with that model, you simulate it, you intervene with it, and if the model corresponds to reality in the relevant ways, you can use the results of the simulation to answer things about the real world, right? And so this is something that you probably all, you feel like you do, but it's still a remarkable capacity that we have. And so my version, much more recently stated, is to reason about the world, simulate it, and interrogate the results of your simulation. And so one of the reasons that I can state this more succinctly is that I'm relying on the fact that everyone here has some idea about simulation, because we've had 40 years of computer simulation, right, which wasn't true 70 years ago, and certainly not 120 years ago. And so this leads to an idea of how we can take this experimental work and bring it into a kind of a computational domain, right? And this comes under sometimes the heading of computational cognitive science, which is trying to use math and programs to analyze how the mind works in very precise ways. And so the first study that I know which did this came from Peter Battaglia, who was at MIT, he's now at DeepMind in London. And he made an experiment. So it's a similar kind of setup. You have a tower of Jenga blocks, like things, and he asked people, does he think the tower is stable or will it fall over, for example? And he said, if you think it's going to fall over, in which direction? So he had a similar experimental paradigm, but he also modeled the thing. And so he built a model of this problem, and the model is what we sometimes call a noisy Newton model. And it's noisy because there's intrinsic uncertainty in a domain, right? So when you look at this block of towers, you don't know precisely where the objects are. You don't know precisely what their masses are. You don't know precisely what their friction coefficients are. And these are the pieces of information that you need to simulate this model. And so what they do is they sample from a distribution, a probabilistic distribution of values. So for example, in one case, maybe the mass of a brick will be 100 grams. In another case, it will be 105 grams. And so once they've sampled a world, then they run a normal physical simulation, the kind that you'll find in a game engine, for example. And so you run many of these simulations, each time with a random initial state, not arbitrary, but random from some distribution. And you get many different simulations. And you collect the results of your simulation, and you use that to answer the query. So this is their model of how they think you're doing it in your mind. And the results show, again, a strong correlation with humans. And so it's a good correlation in the sense that it makes the same mistakes as humans make. It's not always correct, right? And so it's a great paper. I recommend you read it. But the idea here is that you have literally something like a physical simulator in your brain. So just to go back a little bit at my statement, one thing that's different about how I put it versus Craig and Hertz is that I say, sorry, I don't have organisms, or I don't have humans, or I don't have we. And I've left the subject of this sentence missing because I'm also interested in AI. And I think in order to build machines that can really reason about the world, they're going to need to have some kind of faculty of mental simulation. So I gave a talk at Strangely a couple of years ago, and I said, my goal is to build Commander Data, right, from Star Trek. I still haven't built Data yet. But I find Data a grounding target because Data is known for two things. One, he's super smart, he's super intelligent, and also he has no emotions. But for me, the most remarkable thing about Data is that he can interact with the normal world very freely. He can pick up objects, examine them. He's presumably built, or maybe somebody else built this model. For Data to act in the real world, he has to have an intuition about the physics and the dynamics of the real world, right, in order to pick up things, manipulate things. These are really the hard things of intelligence. So maybe we're done. Maybe we can take this Noisy-Newton idea, get our best physical simulator, put it in Data's brain, and now Data can answer questions about the physical world, right? And so maybe we're done. Mission complete. Mission accomplished, right? So the reason is obviously not so simple. Nothing simple. There's many problems. One, what if how do we get a simulator that's accurate? What if there's a disparity between the simulated world and the real world? Also, isn't simulation overkill? If I don't need to simulate, for example, the blades of grass at the bottom of a cliff to know that it's not a good idea to jump off a cliff. So there are all these hard problems with simulation, but I still think there's some intrinsic value to the idea. So there's one problem in particular I've been working on, and it's the problem of causal inference. Right? So here again we have a block of a Jenga tower, but in contrast to the previous example, you can look at this example and you can think about what happened before, right? So in some sense, you can do a kind of inverse simulation. You can say, well, I'm looking at this block, it looks like it's falling over, and maybe a few moments ago, it was upright. And so somehow you're going from your observations of the world backwards through your simulation, or backwards through time, to figure out what is the cause, or what is the state before what I'm seeing. Another example where this pops up is when we need to manipulate the world. So here's a robot called PR2, and it's folding some clothes. And folding clothes is a very difficult thing, because you need to know about the dynamics, the texture, all these things about the physics of clothing. But it's not like you can't just simulate the world and hope that somehow in your simulation the clothes end up folded, right? You have to say, what do I need to do? How do I need to interact in this world to get to some desired end state? In this case, have my clothes be folded. And so I would argue that both of these examples, really they require a kind of inverse simulation, going backwards from either an observation or a target backwards to some input, right? Either the cause or what should I do to create this output. And so in part two, I'm going to talk about my approach, how we're trying to solve this problem. And it's a new approach, and we're quite excited about it. And so the idea, as it says here, is we're going to try and run these programs in reverse. And many people have done things in equivalent in a kind of analogous way, but we're trying to do it literally, to run the programs backwards from output to input. So let's do a small demo. Okay, can you see that? Just about, right? So inverse kinematics is similar to this robot fold clothing example, but just a kind of a simpler instantiation of it. So if you have a robot arm, the robot has joints. And so the joint angles here are theta 1, theta 2, and theta 3. And the hand is at some position in 3D space, right? So this is the Julia language, by the way. I'm going to talk more about it at the moment, but hopefully what I've got here is basically self-explanatory. And so we can construct a function here. It's called the forward kinematic function, and it takes as input theta 1, theta 2, and theta 3, and it outputs point in xy, right? And so this point in xy is where is the hand in 2D space. I've got a 2D robot in this example. So I can evaluate this function, and I can create some random angles, some random thetas, right? Using this rand function. And just to show you that this function works, I apply my random angles. I apply my function to my random angles, and I get out some random point in xy. And I can draw this. I think it's slightly cut off, right? But the point is that I've got a line drawing of a robot arm. But what we normally want is to be able to say, I want to put my hand at some place in space. What should the angles be? Right? So I want to, again, go backwards through my model to say, what is the input that would create a desired output? So I'm going to choose some target, x and y, and I'm just going to add that target to my diagram. And as you can see, my arm, my not very detailed arm, is not reaching the desired target. And so now I'm going to construct this thing called an arrow. And so I'm not really going to get into what this means too much, but an arrow you can think of as a kind of function or a kind of representation of a program. But I'm going to construct an arrow, and it's going to be equivalent to the function that I wrote up here, right? And so this function, again, it just takes in 3 thetas, does some trigonometry, and outputs xy. So I'm going to construct this arrow down here. It's basically a program, and you can see it has a similar type. And just to show you that I'm not lying, I can apply my random angles to my arrow now, and I'll get, again, a random point in xy. Okay, but the magic here is this function invert. And so this function invert is going to take my forward kinematic function, and it's going to return an inverse kinematic function. And now what I can do, and I'm doing some degree of hand waving here, is I can go from my xy position back out to my angles, right? And so I can run this thing, and hopefully it works. And again, I can now draw my scene, right? And so now we can see that the robot is now reaching the desired point, right? And so if that didn't all make sense, the basic idea is that I had this forward kinematic function which took in some angles and said, here is my point in xy space. And now I've inverted that function and said, oh, take an xy and give me some angles which would reach that point, right? And so now I can say, if I had a real robot, I can say, oh, here are the angles that you should choose. Here's how you should change your motors such that you can go and pick up things in real space. Okay, so even if you don't care about AI or human intelligence, you should still care about function inversion, because it really pops up everywhere when you have it as a kind of a hammer. So, for example, if you had a kind of quantum simulator which took in some molecule and said, okay, how efficient would this be in a solar panel? If you could invert this function, you could say, well, I want a highly efficient molecule. Tell me what that is. Or if you took eval, right? So eval in most programming language takes the program and evaluates that, gives you some output, for example. If you could invert that, you have a kind of program synthesis. Give me the program that generated this output. Or if you have a Boolean formula, and you can evaluate to see, is this formula true given the assignment of values to variables? If I could invert that, I have a satisfiability solver, a SAT solver. And as I'm sure some of you know, SAT solving is one of the core problems of computer science. Or another one, if you have a loss function, if you can invert a loss function, you can do optimization. So function inversion really is everywhere. People don't always explicitly define their problems in terms of function inversion, but it really is a core part of many different problems. So the main, at risk of giving too many different examples, the main example that I've been working on is this idea of inverse graphics. So the question that inverse graphics tries to solve is to say, how do you see in the world? And so I'm sure everyone here is familiar with animated movies like Toy Story and so on. And the way Toy Story works, for example, is that they create a 3D model with geometry of the world. They render that, they basically simulate light to construct a 2D image. And so you can think of vision, seeing, as the inverse of that process. I get 2D images into my eyes, and I go backwards to construct a 3D representation of the world. So that's like a very old idea, but we're trying to take that idea literally. So the reason that it's hard, a difficult problem, is because there's lots of information loss in the forward process. So I've got 2 different 3D shapes, 2 different x's, and they both create the same image as an output, right? Because there's some cropping. And at the same time, there's many things which don't create a desired output. And so this is the kind of problem that's hard for normal machine learning algorithms. And so we need a different approach. So fundamentally, why is it hard? It's hard because we're trying to invert a non-invertible function. Right? And so a function is non-invertible, it's called non-invertible, if there are multiple inputs that map to the same output. And it's non-invertible because if I'm trying now to go from output to input, I have a choice, right? So I'm trying to go from y to x. Should I choose x1 or x2? Right? So in some sense, we shouldn't really call it non-invertible. It should be not uniquely invertible. And so our approach is to say, OK, let's parameterize this choice. So we have this thing that we call a parametric inverse. And so we extend the space, right? So we extend the domain with this space called theta. Right? And so now if I choose theta to be 1 for given y, I'm going to get out x1. If I choose theta to be 2, I'll get out x2. So I'm introducing a new space to eliminate this ambiguity. And so this function takes in y and theta and returns x, and it's called a parametric inverse. And so, for example, I'm sure everyone's familiar, so the square function is not invertible because 2 squared is 4, and also minus 2 squared is also 4. And so we can define a parametric inverse which takes in some value y and some value theta, basically 1 or minus 1, and it just returns y times the square root of theta. Right? And so basically, if I put in to my parametric inverse 4, for some theta I'll get out 2, and for some other theta I'll get out minus 2. Right? This is what a parametric inverse is. It parameterizes the space of possible inputs that map to the same output. And we can do a similar thing for addition, and basically all of the common functions that you'll find in a normal programming language. So addition, for example, 5 and minus 5 and plus 5 both add to 0. Minus 6 and plus 6 also both add to 0. But with this parametric inverse, we can vary theta, and we get back a set of different pairs which all sum to 0, for example. And so this is, I guess, the only real equation. So a parametric inverse is a function. So I've got a function from x to y. A parametric inverse is a function which takes in y, a parameter theta, and gives you out x. And the requirement, the constraints on the parametric inverse is that for any theta and any y, the x that I get out should be an element in the pre-image of y. And the pre-image is like the set of x's which the forward function maps to y, right? And so all of these x's which map to y, I should be able to get back going through this parametric inverse. So I'm not going to get into this too much, but I showed you it for addition and I think the square function. But what we want to do is invert big complicated functions. And so we have a kind of chain rule of parametric inversion, which basically says if I have if I have a program and it has like 2 functions in it, I can construct the parametric inverse by parametrically inverting the first function and the second function and like reversing the order. This is the basic idea. Sorry about that. Is it this? So just to give a simple example, here I've got a parabolic function, right? I've got x1 and x2 are inputs, and the output is x1 squared plus x2 squared. And so the way that I parametrically invert this, I take each primitive, I replace them with the parametric inverses, and then just invert the direction of the arrows. And so there are some hard problems that we're trying to solve. It's not as simple as this. You can't just do it in a trivial way. But this is really the general concept. You take a big complicated function, you replace each primitive in that function with this parametric inverse, and then basically revert the flow of information. And so one other question that comes up is like, what should you choose for your parameter values? I said we have a choice with the parametric inverse, but for example, for inverse graphics, for inverse rendering, we want to figure out the most likely scene, the most likely interpretation of the world, not some arbitrary interpretation. And so we're using a combination of parametric inverse, which basically does the inversion, and a neural network which says, okay, of the possible things it could be, of the possible 3-dimensional worlds that could exist, you try and figure out what is the most likely. So there's this kind of marriage of 2 different approaches. And so here's a simple example. It's not the most complicated renderer in the world, but we still think it's pretty cool. So on the left-hand side, we have the observed image, so it's the input to the parametric inverse. And in the middle, you have the output of the parametric inverse. So we have to obviously, I can't show you a real 3D shape here, so I have to obviously render it again. But on the right-hand side, I'm just showing you that the output of the parametric inverse rotated to a different orientation, just to show you that we actually can really construct three-dimensional shapes from two-dimensional images. And so there are other approaches that are trying to do the same thing, and this is kind of an active area of machine learning. But I would say our approach is the only one which we literally take a rendering function and we run it backwards from output to input. And so here are some more examples: a car, a bottle, some more chairs. And it's at least in these examples, it's working pretty well. So that's the basic idea. So now I'm going to talk about Julia very, very briefly. So I did a lot of work in Python for a while, and I just want to give you some reason why I decided to jump over to Julia. So Julia is a programming language. It came out of MIT, and it's designed by people who are really interested in technical computing. By that, we mean numerical computing, scientific computing, but I think it's good as a great general-purpose programming language. So just to give you a kind of a whirlwind tour, this is how I think about Julia. It's like Lisp fast, like MATLAB, R, C, Python, all combined, but not in a kind of messy way. It's like very consistent internally. So the hello world is similar to Python. I can print hello world. People in Julia love to use Unicode, so you'll see lots of pi's and tau's and deltas in the code. We can do function definition, so we have this kind of implicit multiplication by x and 2, and function application as the kind of the normal way. So this is the longer form of function definition. Again, it should be quite explanatory. One of the defining features of Julia is that you have these methods, right? And they're a little bit similar to methods in other languages, but they're not part of an object. You don't have object.call method, but they exist in a kind of external world. So I can say f, and I can define f again, but this time taking as input a float. And so this double colon means x is of type float 64, 64-bit float, and it's returning a string, right? And so I can evaluate this, and I get out x is a float. I can do the same thing for a Boolean. And again, I can evaluate that with true, and I get out, okay, x is a Boolean. And of course, I can create my own type. So Julia, it doesn't have many built-in things. There's no, plus isn't special, minus isn't special. On the other hand, it does have many, many built-in functions, right, in terms of the kind of way that MATLAB does. It has a very large standard library. So I can create my own type. Let's just call it my type. And I'm going to construct an object of my type with input 1. So this x means that my type has one field called x. It's just a struct. So I can now define f to take in a value of my type and return a string, right? And so just to evaluate that, so x is a my type with value 1. And so I've used f many times now. Maybe you thought I'm replacing f, but I'm actually adding more methods to f, right? And so I can look at the methods of f. And so you can see there's I guess 5 here, right? So there's the my type, the bool, the float, and then the two on-typed examples. And so I can look at a more common function, addition, right? Look at methods of addition, and you can see there's a whole range of different ways people have overloaded addition. And this is just in the standard library. If I import other libraries, there'll be hundreds more. And so the way that Julia is based around this idea of multi-method dispatch. You take functions and you overload them. And it's kind of hard to explain why this is important, but once you get a feel for Julia, it becomes like quite an incredible feature for a programming language. So let me just scroll down. And so what I can do is import plus, and now I can add a method to plus with my type. And so I'm just going to add two my types, which means just adding the internal elements together. And so now I can add my type 1 to my type 2. I can do the same thing for multiplication. And so now I can multiply values of my type. One thing I can do now is create a matrix, right? And so a matrix is just in this kind of list comprehension syntax. A, and I can create a vector B, all of my types with random inputs, so like random fields. And now I can try to do matrix vector multiplication. But it doesn't doesn't quite work. It says I need to define 0 for my type. I can go in and I can import base.0, and now I can do matrix vector multiplication of elements of my type, right? And so the nice thing about Julia is that you define a few things for your own types, and then you get a lot of things for free, right, from other libraries or from the standard library. So that's a very fast version of Julia. It's a great language. I recommend you go and check it out. People come to Julia because it's fast, it's efficient, but I would argue Julia is a great language for building your own DSL, right? And so in the example I had before, I had this, I constructed this arrow using invert. So I took in some function, the forward kinematic function, and I somehow converted that to some arrow which I then inverted. And the way that I did this is using Julia's introspection ability. So one of the things that you can do in Julia, which I don't know many other languages that you can do, and you can look at the code that you're generating on the fly. So for example, I made many different functions. I can use this function code load. It's actually a macro, but I'm not going to get into that. But it returns me the syntax of the program that I just wrote. And this is really a syntax tree, so I can go in and I can manipulate this function as I wish. So it has a body, it has a body and a type, it's an expression, it has a head, args, and so on. I can also get the typed expression, so I can say, Julia, go and do type inference and tell me the types of things, right? And it'll give me back the source code, again, in a syntax tree form. This is why it's kind of a Lispy language that I can again go in and manipulate and use. I can even go in and get the LLVM, right, and see what is the code generated on the fly. And so for my matrix vector multiplication, I can again go and get the code LLVM, and obviously it's a much more complicated function, right? And so my main point here is that Julia allows you to really go deep into the code what you're generating on the fly, right? And so when I had built this arrow from that kinematic function, I was going into the code of that function, analyzing the source code, and actually building a computational data flow graph, the kind you'll find in languages like TensorFlow, which I think there's a talk on maybe later today. And then I do all my inversion stuff. This would be super cumbersome to do in Python or many other languages because they don't have the kind of introspection abilities that Julia does. And so if you're building a DSL, I highly recommend you check out Julia. OK, so just about to wrap up. So the main idea I wanted to show you was that mental simulation is this cool idea. It has all these problems. It's very hard. But I think it can offer a way that we can think about a more general kind of human intelligence. To do this, I think we need to invert programs. And I've shown you a kind of a way that we're trying to do it. We think it can scale to bigger programs, and this is what we're working on actively. Both of these things are very hard. Contributions are welcome. If you're interested in this kind of thing, come and talk to me. Yeah, that's it. Thanks a lot. So do we do questions? I guess I could take some questions.
I wanted to ask about your hand waving. So you generated an inverse function, inverse kinematic, and then it looked like you were calling it grand inverse. Is that supplying theta, or is that doing something else?
So the thing about kinematics is that there's many joint angles which reach the same output, right? So if the target is here, my hand could be here, or hand could be here, hand could be here. So rand inverse, it just chooses a random solution. Yeah. Sorry? Yeah. Yeah, effectively we reverse the code of the function. That's basically what happens.
Yeah, going back to your original presentation on the studies of humans anticipating rotation stuff, do you know of any research with non-human participants?
As in animals?
Yeah, presumably.
I mean, there's lots of, there is a lot of work with like monkeys, and they sometimes they measure from their brain when they're reaching, yeah. So there is some work. I think a lot of that work is trying to figure out what parts of the brain are involved in this kind of motor control, for example.
Yeah, I'm just curious whether they would also give a sense of whether they have the same types of models
Yeah.
operating.
Yeah, I mean, there's definitely like lower level things that we do which certainly don't require big simulation, right? You can, swat a fly very quickly. So there's some kind of balance between, a general kind of simulation and when you need to do things quickly, fast response and reaction, and that kind of gradient is a hard question. Yeah.
So in choosing, in parametric inversion and choosing your theta, it seems like you went you probably like analysis and trade-offs to make different machine learning approaches there, but you just went for like a neural net. What's I guess what's the rationale for that?
Why use neural network?
Yeah, and like what other approaches might work there?
So we do a bunch of things. We do like variational inference, and we use a neural network. I guess the way that I think about it is that, so the way that we see the world is driven by physics, right? It's driven by how light propagates around the world, and that's in some sense simple, right? But figuring out the most likely interpretation of the world is complicated, right? It requires data. It requires knowledge of the kind of the distribution of real world scenes, right? And somehow we need to model that with something which is more messy than a program. And so I'm not tied to neural networks, but they work well with large amounts of data. And so that's one of the reasons that we're.
So as a follow-up, what kind of data sources do you have, and like how are you generating data, like training data?
So in this case, we use 3D data sets. But in general, I think that's not really the way to solve the problem, right? Because as a human, you don't really have access to the three-dimensional world. You only have access to images. And so we're trying to think of how we can do this just based on image data alone. But it requires like some significant algorithm changes. Yeah. Any more questions? Oh.
What are some of the hard parts of scaling this?
So basically, as I tried to communicate, the basic way that we do this is that if you have a program and it has all these primitives in it, we invert the primitives and we run the program backwards. And each of these parametric inverses has its own parameter, right? And so you get out of this big program a big parameter space, which is just like the concatenation of all the parameters of all the individual primitives. Now it turns out that on some subset of that parameter space, the parametric inverse is not well defined. So you'll just get error, right? And so it's kind of like there's many ways to go backwards through the program, but some ways are kind of dead ends. You'll get stuck, right? And so the hard part is figuring out how to essentially not get stuck, right? Like what subset of the parameter space is the parametric inverse well defined upon? And so that's the hard part. And to do that, we use like a whole bunch of different approaches. Yeah.
Do you have any code on GitHub or something?
Yeah, so there's code you can try to play with. So the framework we're working on is called arrows.jl. It's in a highly experimental state, which basically means broken. But if you want to try, you can certainly try, right?
When you say you invert the primitive functions, is that happening at the highest level of the Julia language, or do you go which sort of level of code introspection do you go to find those primitive functions to invert?
So there's two steps. So we basically have a language within Julia. And the first step is to take a Julia program, a normal Julia program, and from that extract this arrow program, right, which is a kind of a data flow program. It's like purely functional. It has few of the complications of Julia. And to extract those, we do like a source transformation. And then we invert the primitives of that language. So we have primitives that are well-defined in our own language, and we translate Julia into that, and then we invert that. Does that make sense? Yeah. Yes, I mean, again, it's a bit like TensorFlow. It's a graph-based language. Yeah, it's a computational graph because it makes things easier for us. Here first.
What's the error signal for the neural network? And what is it being trained on exactly?
So the error signal is basically if you start with an image, right, and then so I've got my parametric inverse, right, and I put in as the image the input, and the neural network is also taking as input the image, and it's choosing the parameters of the parametric inverse, right, and then I invert that image with respect to those parameters, and so the error is, does the 3D object that I've constructed correspond to the data that I actually have in the data set, right? So that's one way to do it. That's not the only way you could do it. And there are actually some problems with doing it that way, but that's that's one way to do it. Yeah.
So you were looking at inverse graphics in your talk on Sigma in 2015.
Yeah.
I guess how has that evolved, and how do those results compare to what you're seeing now?
Yeah, so this is a kind of an evolution of that project. So probably most of you don't know. So I had a previous project which was trying to do the same thing but using very different methods. This is kind of like the under approximation of Sigma. So Sigma was a probabilistic programming language, and it kind of over approximates in the sense it considers many possible things at the same time. And that has problems of scalability, right? And this has problems, but like basically I think this approach can scale in a way that Sigma could never scale, right? And so this is really trying to do similar things, but in a way which we're pretty confident we can actually solve to inverse graphics. So in Sigma, I couldn't show you the demos like the one we couldn't do this in Sigma, for example, right? But we can do this using parametric inversion. Yeah. I guess that's no more.